I'm trained as a statistician. I've been in a laboratory medicine environment for most of my professional life, but my training, my PhD is in biostatistics. And I have come to discover over the years that while I've dealt with many very intelligent, bright laboratory scientists, statisticians and laboratorians don't always quite think the same way. Not one's right or wrong, just a little bit different. So I belong to the American Statistical Association, which is it's the society like the AACC for statisticians. And American Statistical Association sells a number of T-shirts that have cute sayings on them because as a society we recognize that we don't quite think like the rest of the world. And I own a number of them, and I'm going to show you at least a couple of them to give you an idea of just kind of how my mind works. So this is the first one. Statistics is never having to say you're certain. We're all about uncertainty, right? I'll give you a 95% probability, but don't expect 100%. And this is the other one. In God we trust, all others bring data. This kind of fits into this talk a little bit in some of the things that Jim said, in that if you want to convince me of something, I need more than an opinion. I want some data to support it. Now, Jim's excellent talk was really pretty broad. Mine's going to be much more focused. I'm going to start with this figure, which is figure 5 in the EP23 document. It shows a flow diagram for what's involved in a risk assessment. So in each of these boxes are one of the sections in section 7 of the document, which is the section on risk assessment. So first you need to create a process map of your total testing process. You try to identify potential failures in each process step. You try to determine mechanisms that are in place to prevent or detect a failure. Then you assess the likelihood or probability of harm for each failure, assess the severity of harm to a patient from a failure, and then you determine whether or not the residual risk of harm is clinically acceptable. And if it's not, then you seek to do some additional risk control to try to bring that risk down to an acceptable level. And once you've decided you have an acceptable level of risk, then you develop your quality control plan. Now, of this whole process, I'm going to focus only on this one. My entire talk will be focused on this because I know that it has the word probability in there, so that might be one clue as to why I'm talking about it. But frankly, I think this is probably the key, isn't it? Assess the likelihood of probability of harm from a failure in a laboratory. So my entire talk is going to be on this. This is another figure that appears in the document. This is figure 6, and it shows the sequence of events that create risk of harm for a patient. It's an example of the sequence of events, and I actually really like this figure. So the idea here is there's some initiating cause that creates a failure mode. There's some probability that failure modes will occur, some frequency of occurrence. And then there's some chance that that failure mode will produce incorrect results. And then there's some chance that those incorrect results will be reported. At the point that they're reported, at the point that they leave the laboratory, that's what creates a hazardous situation for the patient, because now there's an incorrect result out there that might be cause a misdiagnosis, and there's some probability of a misdiagnosis based upon an incorrect result. And there's some chance that that misdiagnosis will lead to a hazardous medical action. And then there's some chance that that hazardous medical action will cause patient harm. So this doesn't talk about the severity of that harm. This is just a sequence of events, the cascade of events that would start with an initiating cause and result in harm to patient. Okay?